Are you working?
Not right now, but we did write a paper together.
Not right now, but these are the
Oh, okay.
Okay, I think we can get started. So we're very happy to have Gautam Satishchandran from Princeton University who's going to tell us about generalized entropy is one of entropy.
Okay, thank you for the invitation. Yeah, so I'll be mostly talking about two papers, which are highlighted here, which are share roughly the same name as the title of the talk. These papers are roughly or basically inspired by and building on some recent work by Edward, Jeff, and this paper very long ago as well. So I just highlight these papers up front. I think I also cite them throughout the talk too, but shoulders of giants and so forth. So good. So this talk is about, well, as you might imagine, generalized entropy. And entropy, and particularly generalized entropy, is associated with subregions of the space-time. And the main ingredients for most of this talk will be, the notion of algebras and subregions. And I'm not going to assume that you all are familiar, well, in particular with algebraic points of view or something like that, so we'll start with the basics. And it's good to, before we get to quantum gravity, just remember what we do in the G Newton goes to zero. So quantum field theory, just on classical space-time background. And in any such space-time, some space-time n, I can, without restriction, to draw some region of the space-time. And consider the so-called algebra of observables in this region of quantum field. So this would involve, for example, the current, the stress tensor, any other. Sorry, I told you I wouldn't draw on the board, and I'm doing that. The algebra, all the observables that I can measure in this region are what I contain in this so-called algebra. Okay. And indeed, in the G Newton goes to zero limit, one can formulate a perfectly satisfactory quantum theory of such fields on a fixed space-time background. So, this is the body of a number of work of about 60 years or so, culminating in this work by Craig, Hagen, Wald, and others. And indeed, it's tempting to ascribe or apply a similar approach to gravitational fluctuations. However, you immediately run into some basic issues. In particular, this region, which I could, in the previous version, I could draw at will. Now, if you want to understand quantum gravitational fluctuation, the region R, at the very least, must be defined in some diffeomorphism invariant way. Okay. Otherwise, when I go to the perturbed spacetime, I have no idea where my region is anymore. Okay. So, an example of such a situation where I do know what I'm talking about is the exterior of a black hole. So this is the space-time, a portion of the space-time of the exterior of a black hole. This is way to the future. I imagine that I got this black hole, obviously from gravitational collapse. That's way, way, way in the past here. And I imagine that this is far, far to the future, millennia to the future. I have this space-time subregion. And indeed, the exterior of this black hole is an invariantly defined region. It's just the path described. And actually, it'll be convenient, and I will do so for the rest of the talk. Well, for all observables that I measure in this exterior region, I can pretend as though the black hole had been around forever. So this is the diagram we normally draw. And the region R is still invariantly defined. It's the intersections of the past and future described. And now when I perturb the space-time, I still know where the region, in particular when I perturb the space-time, in general the horizon might move. But this intersection region, which is defined by shooting light rays from the past and the future, is still invariantly defined. Okay. So, indeed, actually, this region is much better behaved than you might expect. So in general, for a general space-time region, if I did invariantly define this region, when I perturb the space-time, this region will depend on the perturbation in a strong way. So it'll fluctuate just as much as by gravitons or whatever else is fluctuating in the space-time. But without one can show, without loss of generality, one can choose a gauge in which the horizon remains in the background. The location of the background horizon remains the location of the perturbed horizon to first order perturbation. So this is the statement where basically, this is my horizon. The claim is I can choose a gauge in which this perturbed, the perturbed horizon, the location of the perturbed horizon, doesn't change to first order perturbation. So what this means is that the region R doesn't fluctuate at all to first order perturbation theory. And the algebra of gravitons in the exterior of the black hole then can be treated just as if I'm doing quantum field theory with a fixed subregion. So is this clear? I just want to make sure. Okay. So that's the idea. And while this region R is defined up to diffeomorphisms of the space-time, and they're all diffeomorphisms now that preserve the location of the horizon. Okay. And indeed, the diffeomorphisms that preserve the location of the horizon, I should have put the citation also here, because they also did this. Well, the diffeomorphisms that preserve the location are the ones that preserve the bifurcation surface. Which correspond to these, what people call, boost super translation. So if F is a constant, this is just the ordinary, translations of boosts around this surface, but you could also do angle-dependent boosts. It's important that you do it on both sides, not just the right, as well as diffeomorphisms of the bifurcation surface itself. Okay. So this is all just supposed to be kind of review with a little bit maybe philosophy. So is everyone okay with this slide? Also, just feel free to interrupt at any time. I don't need to get through all my slides. Okay. So we'll return back to this statement later in the talk. Okay, so what do I mean by this algebra of observables in our subregion? Well, yeah, in ADS now, this algebra of observables is now just the algebra of observables of gravitons in this region. And one can, there's a preferred vacuum of these gravitons in an ADS black hole geometry, where the state omega, this vacuum, is globally thermal in this subregion. Okay. This is just all to say that this is the canonical thing that you would have done for the quantization of gravitons in this region. And the question is, well, have I found the algebra of physical observables in this right bunch? Okay, so certainly these are all the gauge invariant combinations of gravitons in this region. But have I completed the story? Well, to see why you haven't quite finished the story, it's useful to look at the gravitational constraints. In particular, well, this H is the energy of gravitons, or if I had any matter, the matter on this Cauchy slice, where delta is delta squared here because you're thinking of the perturbation as a first order perturbation. So that means that the energy is a second order quantity. It's quadratic in the perturbation. You integrate it over some spatial slice. This C is the boost killing field. And indeed, the energy of this guy, well, if you plug it into Einstein's equations, is equal to the difference of the perturbed ADM masses of the left and right wedge. Okay. So the insight of some recent work that I highlighted at the beginning was that if I really say that I have the algebra of this right wedge, well, all physical operators must commute with the observables in the left wedge. Okay. In particular, well, this algebra of the right wedge certainly commutes with all the graviton operators in the left wedge. But the physical algebra must also commute with this perturbed ADM mass, which is a highly non-trivial constraint on the algebra. So the way this was done, well, HC fluctuates like in an arbitrary quantum state. It'll have generally fluctuate. So in order to solve this constraint, you'll also have to quantize or the fluctuations of the perturbed ADMS, which is in this work was quantized on L2 of R. And if you do that, then you can straightforwardly solve this constraint, the constraint being, now what are the algebra observables in my right wedge? Well, it's the perturbed ADM mass, that's in my algebra, together with, well, it can't just be the fields alone, because the fields don't commute with the perturbed ADM mass in the left wedge. You have to conjugate the fields in this way, with this e to the I, and explicitly including the Hamiltonian, which wasn't in my algebra to begin with. And if you conjugate the fields in this particular way, this combination commutes with the perturbed ADM mass. Okay, so this is the algebra, physical algebra of observables of our right wedge. We take a double commutant. That's just saying I take this guy and I take arbitrary, matrix elements in the Hilbert space and all limits of such matrix elements. So it's like every observable I can possibly measure with these operators. Okay, so this is a new algebra. In particular, it includes this new operator, which is the Hamiltonian, which wasn't in my algebra to begin with, together with this perturbed ADM mass. And a fair question is, well, what is this algebra? It's certainly different than the one we were considering before. And well, to explain what it is, it's useful to review. Again, I'm not going to assume that you know the different classifications of such algebras. But it's to review the types of so-called von Neumann algebras that you might get, which were classified by von Neumann almost a century ago. So they come in different types, as you can see. Type 3 von Neumann algebras are algebras that don't admit pure states or density matrices. And an example of such an algebra is, let's see, this one. So the algebra of operators just in this subregion is a type 3 algebra. That's because it commutes, every operator is strongly correlated with an operator in the commutant. So, and it's so strongly correlated that you can't assign you can't construct a trace, so there's no pure states, but there's also no density matrix. The analogous or the simpler object that you might be more familiar with is the type 1 algebra. Those algebras admit a pure state, but they also admit density matrices. That's like if I took the algebra of the right wedge and the left wedge. Then those algebras have ordinary, well, you can assign an ordinary Hilbert space to it and an ordinary space. So there's one algebra that's intermediate in both quality and number, which is the type 2 algebra. Those algebras don't admit pure states, but they do have a trace. So one can assign a density matrix and compute an entropy up to a state-independent constant. So this is these traces have a constant ambiguity in them. And if the trace is normalizable, then the algebra is called type 2-1. And if the trace is not normalizable, then, and therefore there's no maximum entropy state, the algebra is called type 2 again. So which algebra do we have? Well, follows from a theorem of Takasaki. Takasaki was in the audience, he should definitely avert his eyes. This is not, he probably wouldn't recognize this version of this theorem, but I wrote it in the way that's most amenable to this talk, which is that if the state that we're considering in the region that we're considering is thermal with respect to this HC, the generator of time translations that enter into this algebra, then the algebra that we got is actually of type 2. So before, without the dressing, the algebra was type 3, but now it has changed type. And indeed, just from this fact alone, that means that we can compute, we can construct a trace and compute entropy. The trace takes this kind of compact form here, which it'll be useful to, because we're later going to generalize this. The trace here has an expectation value with respect to the vacuum state that we constructed here, but it also has an expected value with respect to what's the zero element or the neutral element of the group R. Remember, the Hilbert space, I can go back, is quantized on L2 of R. The zero R here is the neutral element of that group. So in terms of, if I Fourier transform this is an integral over all of x. Okay, so it's a delta function in the t variable, or integral over all of x. And the claim is this satisfies the properties of a trace on this algebra. And indeed, if you look at the von Neumann entropy of any semi-classical state, so where this wave function on the L2 of R is sharply peaked in time, then the von Neumann entropy is the generalized entropy up to a fluctuation term that depends on the A. Okay, so that's all review. So that was the status of things, when I guess, arrived at Princeton. And my office mate was, Sam Loyloiser, and I was asking Sam, well, what's the latest, what's going on? And he basically explained to me in not so many words what I just told you. And my first reaction was, well, what about asymptotically flat black holes? Or what about any other black hole in which the natural vacuum state is not precisely thermal? Do we get a similar conclusion? Indeed, you can follow the same, and we will follow the same exact analysis. But the question, I had at the time was, well, what if, how could you conclude the type of such an algebra from that construction? So indeed, Einstein's equation, just as before, relates the energy of the field to the perturbed area, the energy of the gravitons to the perturbed area and the perturbed ADMS. So I'm just writing that out for you. So this HC that I've integrated here is, again, just the total boost energy of the gravitons on this slice. This is going to be the integral, this integral is going to be the sum of two boundary terms. One boundary term is just a perturbed ADMS. And the other boundary term is like a perturbed area. Basically, if I took this slice and I hit it on this past horizon, then at any finite u, affine time u, then it looks like this. But then you just take the limit as this perturbed charge goes to the far future. The basic point is that this thing is just as much of a commutative as what we discussed before, so we're going to get a similar constraint just as before. Okay. So indeed, I can quantize gravity, the gravitational fluctuations in R. I can demand that it commute with any perturbed charges in the complement region, just as before, and I can construct an algebra of dressed observables, just as before. Okay. But one cannot directly determine its type, because as I said, the vacuum state, or no state in the Hilbert space that I'm considering, is thermal, precisely thermal in the exterior region. Okay, so indeed, right, just to remind you, the vacuum state for gravitational collapse is the Unruh state, which is thermal up here. But as I go to describe, but isn't thermal totally in the exterior region. The black hole is radiating out into empty space. Okay, so what do you do? So, well, at that point I was, maybe convinced, okay, maybe this type 2 stuff just doesn't make any sense. But Sam convinced me that, maybe we should try a little bit harder than that. And the way to actually see what's going on, or the simplest way, is to look at this algebra of gravitons and write it in terms of initial data. So what do I mean by that? To take your favorite metric perturbation, smeared into some space-time region, and propagate it backwards. Okay, into the far past. The algebra factorizes into an algebra on the horizon, together with an algebra at infinity. Okay. So this is, I should say, a fairly non-trivial statement, because there are null geodesics that just go around the black hole forever, right? So you really need to show that the operator, that's an unstable surface, so you really need to show that the operator ultimately decays. And there's no flux at I minus. Okay. So why is this really useful? Well, not only does the algebra factorize, but so does the vacuum. And the vacuum, the Unruh state factorizes into a quantum state, into the vacuum state at scribe, and a mixed state on this past horizon, which is exactly thermal. Okay. Indeed, it must be this thermality, and when you propagate it to the future, ultimately becomes the thermal Hawking radiation in the far future. Okay. So what does this mean? Well, the algebra, this factorization, now from the point of view of initial data, you can see why this algebra is type 3. It's a tensor product of a type 3 algebra, which is the thermal radiation here that's entangled with the interior of the black hole, together with a type 1 algebra, which is the vacuum. This vacuum state is pure, so this algebra at scribe is a type 1 algebra. Okay. And indeed, you can take that constraint that I wrote and write it into the sum of 3 constraints. Yes. So good. So well, it's thermal when restricted here, so it's automatically empty, but it's also entangled. If you write this whole initial data surface, it's all the operators here are strongly entangled with operators here. So you can take that constraint that I wrote before and split it up in terms of constraints on this initial data surface. And so to claim if you sum up this guy, this guy, this guy, you just get back the constraint that I did before, but I split it up in this way. And you get a constraint here. This is a Hamiltonian that generates boosts on this initial data surface, and that's the difference of these charges, these boundary charges living here and here. These are just the limits of those charges I introduced before in the far future and past. You can show that this perturbed charge here matches on to the perturbed ADM mass at I minus. And the perturbed ADM mass at I minus is related to the perturbed ADM mass at spatial infinity by the generator of time translations at scribe. So it's just splitting up the formula that I gave before, but it's now useful because I split up the initial data. Okay. So the algebra on the past, the algebra at scribe is type 1. And the flux here, the flux, this HC, which we would have wanted to include in the algebra if we're trying to commute with the charge in the far future, this HC is the flux that just gravitons in this region over scribe. So indeed, this HC is already in the algebra of observables here, and indeed, starting with a type 1 algebra, the constraints basically have no effect. The algebra is still type 1, even after dressing. And indeed, nothing happens to this algebra at scribe. All of the interesting stuff happens to the algebra on the horizon. The algebra on the horizon is type 3. And what we want to do is have it commute with the generator boosts plus this perturbed charge in the right, which means that the generator boost is not in my algebra. That involves both the operators on the past horizon here together with operators over here. So that is genuinely now a new algebra, which indeed by Takasaki's theorem is type 2. So the full algebra is type 2 infinity, so it's a type 2 algebra, which is this, which is just really coming from the degrees of freedom on the horizon, together with a type 1 algebra, which is unaffected at all by the dressing. And indeed, so really you should think, so the reason I presented it in this way, you should think that these arguments only use two facts: the symmetries of the horizon and the properties of the vacuum near the horizon. Okay. So given those two facts, one might expect that the arguments that were being used earlier by Edward and Jeff and others in the ADS case can be immediately generalized to arbitrary stationary black hole spacetime. Indeed, every stationary black hole spacetime will contain a horizon which is exactly thermal, and therefore yield after dressing a type 2 algebra. And indeed, that's the claim. So the claim is that hopefully you can see how to generalize these arguments now that you've seen it once. For any stationary black hole, the algebra of observables in the exterior region is type 2. It's type 2 actually infinity, and hopefully that's physically, makes sense because the area, what we're doing is quantizing the fluctuations of the black hole, which in the area can, get perturbed up and down. So there's no maximum entropy state for these objects. Okay. Any questions so far? Yeah.
You define cross product with some automorphism to be interrupted. Is it true that any cross product is automatically type 2? Or
Great. I'm about to get to that.
Okay.
Could one summarize what you're doing as essentially cross product with a different outlined charge that's not just the but also these additional charges?
What additional charges?
Like this.
No, so yeah, maybe I should make it clear. So I wrote down a bunch of charges, right? Let's go back. I wrote down a bunch of charges, but this is already in my algebra, okay? And so this flux is already in my algebra, and all of these charges are connected to each other, right? By different fluxes, right? So when I'm saying I'm commuting with this guy, and I include any one of these charges in my algebra, I get all of the other charges in my algebra. So the point is that if you quantize this guy, and you demand that you're commuting with this guy, I claim you get a perturbed ADM mass at I minus, you get the perturbed ADM mass at spatial infinity, those are all for free. So remember that these formulas are all, there's enough inequalities here that all you need to include is one charge and commuting with the charge in the left region.
And that one charge is enough to essentially make a cross product.
Exactly, yes. That's the idea. Good. So before I get to Arvin's question, let me first talk about de Sitter spacetime, which is the other reference I highlighted in the beginning, with Edward, Jeff, and Roberta Long. Okay, and so what's the story there? Well, this is de Sitter spacetime. Now the region, the subregion, is defined by, well, if I have an inertial observer in de Sitter, it's the domain of influence of that observer, but you should think that all of the statements I made about defining the subregion, in particular the horizon is not fluctuating, at least in first order, is exactly the same. But we run into a different issue, which we're going to have to contend with in this talk, which is that in a closed universe, the Hamiltonian, which played a central role in every other thing I just talked about, is a boundary term. And in a closed universe, so a universe without a boundary, the Hamiltonian must vanish. Or in the quantum theory, we require that all physical observables in our algebra commute with the Hamiltonian. This is going to run into a lot more, that's a much more significant issue than anything else I've just discussed, because that is going to, totally trivialize the algebra. The only operator in my graviton algebra that satisfies that is going to be the identity. And to remedy this, these authors endowed the observer, so the observer I gave you here in this region, they endowed the observer with some degrees of freedom. And the idea here was just to avoid this issue. Okay, to obtain a non-trivial algebra, and such an algebra, I guess we'll denote as, addressed algebra of some kind. I'll explain what that is, but with this observer symbol on the top to explain, to mention that observer is explicitly put in. So that is a little bit different than how we normally do physics. So normally we don't put an observer into the system that we're studying. And indeed, I guess it's all the rage now. It's not something we've normally done, so we should be careful moving forward. So there's a couple questions you might ask. Well, first, what is this algebra supposed to mean? Let's say I do construct a satisfactory algebra of such a kind. What could it mean? And furthermore, this is going to be a question that I'll return to several times in the talk, how should this observer be modeled? Okay, so you could imagine that you could model the observer like, this piece of chalk, or with a standard model, or an atom, or so forth. But, it's going to be really complicated if I use the standard model, or use an atom, and so forth. Those are a lot of degrees of freedom. And in particular, you don't want, if you make the observer too complicated, you end up studying more about the properties of the observer than of the system that you're studying. So you're trying to find the simplest model possible that that leads to a non-trivial algebra. Okay. Yeah.
So this issue of triviality algebra is not a closed universe problem generally, it's just a de Sitter problem, or like something related, because there has to be an isometry or something, right? Like in general, these things can.
Yeah, so indeed, so when you don't have when it's not an exact isometry, you can, there are essentially, the gravitons that you have can be possibly used to dress to. It's not entirely clear that solves the problem. It's just not in your face as much as in the de Sitter case.
How do you consider it? I guess what's the quickest argument that the algebra is trivial? That's it.
A quick argument would be to quote a theorem or something, which I could do. I mean, so there is all of my operators, so this generates time translation is a static fashion. You can show, or I think it's in maybe a talk or something, that the action of these translations are guide. You can basically, any local observable can be reached by another observable by, sufficiently acting with these time translations. So indeed, this ergodicity, I think generally, is the statement that they use in CPW, for example, CLPW to claim it. But I think you can also just see, any local graviton that you have in the region. Imagine any local graviton in the region. Now you translate it up and down. It's not going to be invariant. So you want something that's invariant in this time dimension, but then it just can't decay.
Imagine something that's smeared all the way.
Yeah, but you want the graviton field itself to be time translation invariant.
Right.
Which means that it just cannot decay in the far future of the past. Yes. Okay. So now, the question that we'll be returning back to in this talk is how should the observer even be modeled if you want to achieve these conditions? Well, to obtain a localized observer with a well-defined static patch, so if you consider a quantum mechanical observer, in general, its wave function will start to spread. And so you need to control that if you want to make sure that it has a well-defined static patch for all time, at least in the semi-classical limit. So first, we don't want the observer to not react too much on the space-time, so that's this condition. And in order to have a well-defined static patch, we need the constant wavelength of the observer to be much smaller than the de Sitter length scale, which means that the energy of the observer must be some parameter m, which we're going to take to be such that if you take the limit as m goes to infinity relative to L, the de Sitter length scale. And then we're going to, well, that's just the background value, and then we're going to allow for small fluctuations of this rest mass. So these Q are order 1 fluctuations. They're order 1 in M, but also order 1, obviously, also in G. And so we're going to quantize these fluctuations of the observer's rest mass with a conjugate clock on this L2 Planck space. Okay. So again, this is just review, and we'll get to Barbara's question in a second. So now the constraint doesn't trivialize as badly. Now we get that the perturbed charge, now I'm doing this trick where I'm just going to evaluate things on this initial data surface here. So that's not a good diagram for the center. So I'm evaluating the constraint on this surface just to keep the discussion symmetric from before. We're now, what I want is to commute with the generator time translations in my region, but normally, well, there would have been nothing here on the right-hand side, but now the observer energy explicitly enters, which enters from I minus down here. And when well, you should see, well, the arguments are exactly the same as before. The algebra of observables that commutes with HC plus the energy now of the observer is a type 2 algebra. And if we bound the energy of the observer from below, this yields what's so-called type 2-1 algebra. The reason is because if I bound the observer energy from below, physically you should imagine that if I bound the energy of the observer from below, that means the area, returned area, is bounded from above. And so the algebra is type 2-1. You can explicitly see that the trace that I gave you before is now normalizable. You don't have to follow all the manipulations, but this trace I gave you before ends up being an expected value of this projector on the positive energies together with this thing that entered from, well, this is the thing that entered from from the formula of the trace, and that just enters here. And the projector, if the projector over positive energies wasn't there, that means this integral will be over all Q. But now the projector is here, so it bounds the integral in Q, and this decays at large Q. So this is finite. And the algebra, therefore, admits a maximum energy state. Okay, so the questions that remain, or we'll discuss in the talk, is what are the full group of constraints on this algebra that follow the same rules of the game as I've outlined so far? Does the algebra, so let's imagine I do get the full group of constraints. What does the algebra remain type 2? When we impose these other constraints, it's closer to what Arvind was asking. And indeed, after we do all that, does the algebra, the static patch, remain type 2-1 after we impose this? Anyone confused about the questions? Okay. So let's discuss a constraint that wasn't explicitly considered in the literature cited up to now. So in addition to perturbations of the area of the horizon and so forth, gravitational perturbations will also perturb the angular momentum of the horizon. You should think so. In the previous literature that I cited before, we all restricted to states which were in the case where, like for the example of the black hole, we restricted to spherically symmetric states, or to in Kerr, we for example restricted to axisymmetric perturbations. The reason before that is that this H, which is the generator of the rotational isometries, is it's an eigenstate. in that case, and we can avoid the rotational constraint. So what I'm now doing is I'm imposing the rotational constraint. I'm allowing for all perturbations, not just the spherically symmetric ones. And so
you're saying that secretly there was this assumption?
no, it wasn't secret. They said like they restricted. Well, the claim was that this doesn't change the story. That's what I'm checking. But they explicitly restricted to, for example, rotational invariant. So like, well, you can't do that in gravity for gravitons, but if you put matter fields, you can restrict the spherically
So you're
symmetric.
saying it's inconsistent to consider all states that
Well,
not
if you
satisfy this, but only consider.
yeah, indeed,
parts
like
of
you
the
just
invariant?
yeah, just look at it. So if you don't restrict to you want your observables to commute with the perturbed angular momentum of the left wedge, right? So you want you want to satisfy this constraint. If you don't quantize the charge in the angular momentum of the right wedge, so which is what you can explicitly choose not to do, then you have to restrict to eigenstates of this H, which are eigenstates of the angular momentum operator of the graviton and matter fields. So if you restrict to spherically symmetric perturbations, then you can satisfy this constraint without quantizing the perturbed charge.
That's one way, but and I don't know if this, another way I could imagine is to somehow choose states such that this calcium does not remain around as G essentially zero. I mean, I don't know if that's possible, but.
I don't think the gravitons will always perturb the black hole or in a.
No, but this is second order G, right?
Yeah.
Second order slower than G, right?
Yeah, so the gravitons are entering this expression. This is the angular momentum of the graviton.
Right, and it's, so, because it's proportional to G, you may imagine that at G equals zero, this calcium is now around.
Well, yeah, so the claim is that this is as quadratic in the gravitational perturbation as the, as the total energy. So it enters at the same order in perturbation theory.
Okay,
Yeah, I should be clear, like this was stated in the paper. I mean, they stated the constraint and then said we're going to restrict to spherically symmetric. There's no issue with that. Okay, so what do we want to do? We want to then, to actually take into account this constraint, we want to quantize the perturbations of the fluctuations of the angular momentum. We can repeat the same approach where this mu here, so we want an L2 of something, just as before. But it's an L2 of the group, where the group is either SO3, for example, if we're doing a black hole, a short-short black hole, or U1 if it's curved. With respect to this mu is now a measure on this group, on the isometry group H. So it's the variant R measure with respect to the group. So there's a canonical way to quantize the fluctuations of the angular momentum. And then the question is this algebra that we had before type 2? So I should now just answer your question from before, which is that if you don't impose this R constraint, and you did impose just the isometry, I won't present it, but you can show that the algebra remains type 3. So the R constraint, I mean, it's actually like, the previous authors, including myself, were very right to, restrict attention to this constraint, the time translation constraint. It's the most important one to get the type 3 algebra to become type 2.
So, but specifically was more formally speaking, if you have our.
No, it's not.
It's not guaranteed.
It's not guaranteed.
It's just guaranteed that it's not type 3 or something?
No, it'll remain type 3 generically.
Okay.
It's
Cross product in general has nothing to do.
has absolutely nothing to do generally with
Either or outer.
even if it's outer, then sometimes you'll get a type 2 algebra,
Okay.
but not general, right? Okay, so now what do we have to do? Well, we have to construct a trace on this algebra as before, and indeed, you can generalize Takasaki's theorem. So remember, Takasaki's theorem was just for the group R, but you can generalize Takasaki's theorem to include any compact group. So this generalization was with my collaborator Mark, together with his these other authors, generalized this theorem to arbitrary compact groups. This proof actually, at the setting of this theorem, was a bit overpowered than what was physically or necessary for the context that we had in mind. So it's actually a much simpler proof, or at least shorter, in this paper here. But the punchline is the following: is that the trace that you get on this algebra is of this form, which hopefully looks familiar. It's almost exactly the same as before, but now it has an extra expectation value with respect to this vector E. And the vector E here is we have a Hilbert space of all elements of the group. E is the neutral element of the group. So it's the zero rotation state. A neutral element with a wave function, which is just a delta function at that neutral element.
Just to make sure, second order here is not second order in G.
No, yeah, gravitons are root G, so it's order G.
Okay, so there's only one power counting is G, and then all the perturbations are root G.
So the gravitons come in order root G, and then this constraint is order G.
Okay, so I think what Alvin was asking earlier is that in CLPW, they took G to 0 and strictly G strictly to zero. So then naively the second order Gauss law will be gone. And therefore they need to, they have to choose a particular state where the constraint is still there, it's strictly G to 0. So I think Alvin is asking, so do you do the same thing? For angular momentum, you choose a state where the angle fluctuates.
Yes.
Order 1.
Yes, that's right.
Okay.
Yeah.
Okay, and in that context, you could maybe choose not to make the sort of the angular momentum part fluctuate. But the total area can fluctuate. The goal of that would be to allow arbitrary states, but still at G equals 0 only maintain formulas.
So all the formulas I get are exactly equivalent to the formulas of CLPW. So I don't think there is a way to do that in a way that makes sense. I mean, this was hopefully I made my approach clear, but I wouldn't say that there doesn't appear to be a contradiction between. I think they write down this formula. But you can, I guess, ask this about a later formula that we will get also. Okay, so good. So indeed, we have a trace. The algebra is type 2. That means that we can write down the entropy, and indeed the von Neumann entropy is again the generalized entropy. But now we should revisit the case of the Sitter space-time. So to satisfy the rotational constraints, in addition to having some energy which matches on to the perturbed area at I minus, the observer must also have spin, and this spin, denoted as L, matches onto the perturbed angular momentum at I minus. Okay, so if we then just simply follow what we said before, so we're going to project onto positive energies of the observer, we can check the trace of the identity. That's the key thing to whether the algebra is type 2, type 2-1. And indeed, it's hopefully clear to see that even after projecting onto positive energies, this object here remains finite. That's the trace that we got earlier. But now we get this expectation value with respect to the neutral element. And recall the wave function of the neutral element was extremely not normalizable. So it would appear we get a contradiction, or something totally different than what we had before, which is that even after projecting the dressed algebra, the entropy is type 2 infinity. Okay, so I would say, so this is why it's really important to ask the question, what's a physical model of the observer? For any physical observer, the angular momentum, so what we did wrong here is that we didn't model the observer correctly. And the degree to which the error of that, of the approximations we made us get this unphysical result. So in any physical model, the angular momentum is not a zero number. The angular momentum of the observer will contribute to its total energy. And the trace now gets an extra contribution, the trace of the identity gets an extra contribution, which looks like, e to the minus the energy, the rotational energy of the observer. So what we find is that the trace is normalizable if and only if the norm of this guy, this state, hopefully state, is normalizable. Oh wow, I said normalizable if and only if is normalizable. That's not good English. So anyway, so this is satisfied, one can check. So now this is a real question about how do you accurately model the observer, which is this, you can check that this is satisfied for a large class of physical bodies. Indeed, if you look at an isotropic body, rigid body, which is a simple example that I can find in the slide, then you can check that this state is finite. Even for anisotropic bodies, you can check that the norm of this state is finite. But indeed, this is now, I guess, it depends very strongly on the model of the observer you have. For example, if you model the observer as a fluid, a ball of fluid or something, checking this condition is much more common. Because the dependence of the rotational energy on its angular momentum depends on the viscosity of the fluid and so forth. Okay, so now let's go back to the last, what I said at the beginning. Well, the R is an invariantly defined subregion. And we can generally find, we will generally find additional constraints than the ones that I mentioned from the other large gauge transformations that can't be split into transformations of the left and right separately. For example, gravitational perturbations and you have matter falling into the black hole will fall into the black hole in an angle-dependent way. It won't fall all spherically symmetrically. The flux of energy at those angles generates angle-dependent boosts of both the left and right wedge, and acts unitarily on the Hilbert space that I gave before. So, the flux of these angle-dependent energies, boost energies that I mentioned before, can be expressed in terms of the difference of these perturbed charges. And it depends on if one takes into account this constraint, which is of a similar nature to the kind that I said before, one could wonder, does the algebra remain type 2? You could also, the question also could arise is, could I even avoid this constraint altogether? And indeed, this is, it is possible, but you wouldn't want whether or not the algebra being type 2 to depend strongly on exactly how you take this limit. So that's the condition that we're going to ask for the rest of this talk, which is, I guess, in the next 10 minutes. So in order to leave time for questions, I'll just kind of go over it in, briefly, which is that the major difference, if you really do want to take into account this constraint, what you're doing is you're looking at the algebra, all the boost super translations, the Hilbert space of all boost super translations in your region. And there doesn't, since this is an infinite dimensional space, there doesn't exist an invariant R measure over an infinite dimensional group. So that's the first issue that you run into. Nevertheless, what you can prove is that for any Gaussian measure, which you can roughly think of just as defining relative to some choice of action, there always exists a Gaussian measure. Indeed, there are many such choices of measure that satisfy these three properties. The first is that this Hilbert space that you construct relative to this measure admits a unitary action of all of these charges for arbitrary smooth f. And indeed, you can change the degree of this regularity if you want. And the amount, you should think that I have a lot of freedom in this choice. The second is that you can choose this action to be rotation invariant. So the full Hilbert space can be quantized as, we don't have to redo the quantization that we considered before, can be quantized in this way. And the last and the most important for this discussion is that this Hilbert space always admits a neutral element, weight, just as before, with a wave function that's a delta function with respect to the neutral element, and now it's a delta function, relative to this vector terms. Okay, so given these three properties, it immediately follows that the algebra with respect to the dressed observables in our subregion is type 2 with this trace. Okay, so hopefully you don't have to think too hard. This looks exactly like before, but now we get an extra expectation value with respect to it. Yeah. Okay. For any black hole spacetime, the algebra remains type 2 infinity even with all these constraints, and the von Neumann entropy of any semi-classical state is the generalized entropy. So in our last slide before I conclude the talk, is now, given this constraint, let's revisit the discussion of de Sitter spacetime one last time, which is that what is our observer? Our observer is an inertial spinning body with energy epsilon and spin L. And in principle, a model of the observer, for example, if I had my fluid that I was talking about earlier, would have additional properties such as mass multipoles in every element. Similar to the total energy, the tidal field of these multipoles will perturb the horizon in an angle-dependent way. Okay. So, and indeed, this actually is in the GR literature, an old story, which I think within the context of what I'm talking about with respect to these charges and so forth, go back to these papers by Ashtekar in the 90s, but also revisited in this recent paper by Fischler just a couple of years ago. But indeed, what's going on? Well, now I've listed the properties of the observer and how they match the charges. The energy perturbs the total area of the horizon in exactly this way. We're now accounting for its fluctuations in the rest mass, and now it's also its rotational energy. The angular momentum perturbs the angular momentum of the horizon. The spin perturbs the angular momentum of the horizon in this way. And now the mass multipoles of the observer perturb the area of the horizon in this angle dependent. And indeed, if these mass multipoles were genuine zero modes of the theory so it doesn't contribute to the energy of the observer, then the trace of one would be again infinite, and the algebra would be type 2 infinite. Okay. So what are we missing? Well, we have to recall that the observer is a compact body in spacetime. So in order to be compact, it must be held together with some binding energy. And the binding energy must be non-gravitational, otherwise it would become unbound in the limit as g Newton goes to 0. Okay. So we need to actually have added some binding energy of the observer in this story. And in general, the fluctuations of the multiple moments of the body will change the energy of the observer. For example, if the observer is at a local minimum of its total energy, the binding energy dependence on these charges is very simply related. In general, it will be a very complicated relation between the two. but for example, just in this context, and indeed, in that context, you can check that the norm of this state ultimately is normalized. So the algebra of observables now is seen by an observer with now all of these degrees of freedom is type 2 left. Okay, so with that, I think I'll end my talk and just say that, well, what this generally shows is that there's the von Neumann entropy of the algebra of physical gravitational dressed observable in the exterior of the black hole, where the de Sitter static patch is equivalent in this sense to the generalized entropy. And what we needed for this was a proper accounting of the degrees of freedom of the observer in taking into account its contributions to total energy. And these results in total, at least to me, suggest a very deep and very unexpected. I'm still surprised, I guess, even though I've written a couple papers on it, the connection between the physical observables of quantum gravity and the generalized entropy. And indeed, I can't come to San Francisco and not even mention the bridge. So this seems to these two facts or these two things have been studied, in completely different contexts in general, and the fact that there is a connection, I think, is worthy of further explanation. So with that, I'll end my talk. Thanks.
Any questions for speakers?
Too clear or unclear?
And this is really
Yeah.
deep, I think, but your G is S cross, your
Yes,
product with H i's up.
yes.
But, so you brought at the very beginning, you have to consider sigmas that preserve the surface and product.
Yeah.
It has two but the rest, they don't have to be isometric, you just want the homomorphisms to preserve your region.
Yes.
But at some point, your G became the S2
There was no
isometry.
No. It's
Sorry, S.
So we ignored all of these guys that weren't the isometry. Yeah.
But there are other things than that that are also not isometries.
Well, these are the large. There are diffeomorphisms that don't generate charges. Those are small gauge transformations, and then there are large gauge transformations that correspond to physical charges on the boundary of my region.
In this case, it hits the boundary.
Hits the boundary, non-trivial, but preserves the location of the horizon.
Hits the boundary.
So indeed, as I said, there also are diffeomorphisms of the bifurcation surface, for example, that aren't isometries. But you can check, well, there's two facts. One is that if you look at the flux associated with those guys, they involve both the first order field and also the second order graviton. So they don't impose constraints entirely on the first order field. And indeed, I don't know if this is an accident or not, the diff S2 for non-isometries is not unitarily implementable on the Hilbert space of gravitons. So these facts mean that, well, this statement and the one I just said just now, I don't know how related those two statements are. That would be interesting to understand better. Yeah. Sure. Oh, sorry. Yes.
So here was the question about whether considering charges don't factorize between left and right, essentially.
Well, all of the charges. So none of the fluxes can be factorized into that I've been considering, even the angular
So
momentum.
what was the new question that this was trying to address?
Oh, so this is stating that, so we before considered the constant boosts and the isometries. So now what I was looking at is the charge flux relation for the angle dependent boosts. So these are a different set of transformations that act unitarily on the gravitonic Hilbert space. But this H, just as similar to the angular momentum and the boost energy, this H cannot be factorized into an action on the right wedge and the left wedge. So this H is not in my algebra initially of the graviton field, right? Just like the boost. Okay, so now if I want to solve this constraint, this adds a new operator into my algebra, which is the one that generates both the right and left.
And sorry, so why did this, go to the next slide, why did introducing this measure,
Yes.
can you just summarize like how that helps?
Yeah, so you want to quantize this infinite dimensional space. So this is, any function of angles, not just the constant one. So the constant one is a one-dimensional space, and we can just quantize that by L2 of R. So you want to do something like L2 of S, where S is arbitrary functions of angles. Okay? L2 of S doesn't have a canonical measure on it. So because it's an infinite dimensional group. So you want to have a construction that kind of is totally independent of my choice, because that's an arbitrary choice that you want. You want your choice to be such that you include as many charges as are physically relevant. Okay? But you don't want it to depend too strongly on anything else. So indeed, what we show is that for any choice of this thing, this is a trace of the algebra. And that's the non-trivial statement. Yeah. Sorry, I probably went over that a bit too fast.
Okay, there are no more questions. Let's thank the speaker.